Okay. So today, what I'm going to try to describe is something about the scientific method, and with of course with a bias towards astronomy and my experience rather than the biological sciences, the physical sciences. It's a great honor to be invited to give the 100th lecture of the Sri Lankan Literary Society, and I hope you enjoy it. I am starting here. So I'll start by describing what the scientific method, as I understand it, is a method that keeps changing as we get new observations, right? So basically, first observations first lead to empirical models that and may break through to mathematical theory. Adequate logical simplicity is always favored over more complex constructs, and I'll give examples. And unexpected observations or results are always welcome as it leads to new discoveries and progress in our scientific understanding. That's a sort of a general statement about science in general as I understand it. And to talk about what model it is, how modeling works, let's consider you try to throw a fish net into the sea to catch fish, right? You get all the fish that you come from the sea and you measure them and you find that they're all larger than 2 inches. So you might conclude that all the fish in the sea are more than 2 inches. But if you find a few smaller fish, you might realize that your inference is just because your net has 2-inch square holes and smaller fish would have escaped. And you get a finer net, you might catch smaller fish, but if you get a solid net, you might not catch any fish. So I think that's a good example to think how science uses models to understand the universe. So let's look at models of the universe, which is the topic of our discussion today. Science understands the universe via observations. Understand is presented through models which appear to fit the observations. Initial models were pure empirical descriptions. When the models were formulated with mathematics, like by Newton, we got the ability to make predictions. When the predictions were observed, the model got recognition as sufficient for the current understanding. And as we get more precise observations, we needed to get mathematical models to evolve and improve. So before discussing the nature of the universe, I think it's necessary to get some perspective of what space-time and life on Earth is. And I suggested a video called Cosmic Voyage on the WhatsApp group. I hope you all have watched it because that would give you a perspective of how small we are in both space and time. I'm not going to show that video. I will just briefly discuss it. One is distance. And we can talk about astronomical distances by the time it takes for distance to be traveled by the speed of light. So the diameter of the Earth would be only 0.04 light seconds. Moon would be 1.3 light seconds. The sun would be 500 light seconds. The solar system is 10 light hours across. Proxima Centauri, the closest star, is 4.3 light years. The Milky Way galaxy is 100,000 light years across. Andromeda, which is the nearest external galaxy to us, is 2 million light years. And the cosmic background radiation is 13.4 billion light years. And that is when that light left it, and currently about 45 billion light years away. So you can see that we are a very small part of space-time, space at least, according to this. And there is a nice powers of 10 video you'll find on YouTube, which describes this whole journey over 42 orders of magnitude. So let's look at cosmological time. That's the space and time. Now, we know now that the Earth is 13.8 billion years, but as I say, not many people can comprehend what 13.8 billion years is. So what I'm going to do is divide it by 31.5 million seconds that each year has. And then I will call a cosmic second to be 437 years. So that way I can look at, this is a concept that was brought by Carl Sagan in his video series called Cosmos. And I think it's one of the best ways of looking at what time is. So if you take one cosmic second to be 437 years, then human history is just 15 cosmic seconds. Homo sapiens have been here for about 10 cosmic minutes. Dinosaurs went extinct 42 cosmic hours ago, which is 66 million Earth years. Solar system was formed 4 cosmic months ago. So both time and space, when you look at it this way, we are living in a flash of cosmic time and a tiny place in space as well. So this is a sort of illustration of what the cosmic year would have been from the Big Bang on January 1st to the extinction of the dinosaurs on December 30th, and finally the Great Pyramids getting formed 10 seconds ago before midnight, and now at midnight. So you can see that the human civilization, or the period that we know and historically documented, is only about 10 to 15 seconds of our history of our universe. Okay, the next thing to do observations and make is you need a set of units. Now, all of you would have, I'm sure, studied the SI units in your school, school days and maybe university. And there are 7 units from the meter, kilogram, a second, ampere, Kelvin, mole, and thing. I don't think many of you, and I had to admit, I didn't know either, that these quantities, which were basically the second being the unit of time, unit of length, kilogram being the unit of mass, ampere, Kelvin, mole, and the candela being a unit of luminosity. That's in 1983, I know that the second and the meter was redefined. But to my surprise, when I was preparing for this lecture, I found that all the other units also have been redefined. So no longer is a kilogram in a lab in Paris, which defines a kilogram. Now what has been defined as a kilogram is the Planck's constant, being a constant. So those days, the second was defined by a frequency of cesium. The speed of light was defined to be exactly 299,792,458 meters per second. And now to define the kilogram, it has exactly defined the h, the Planck's constant, to be a constant. No error bar that defines the kilogram through the constant there. Elementary charge has been defined. Boltzmann constant has been defined, and that defines the degree. Avogadro's constant has been defined as a fixed number of 10 something to the 10 to the 23, and luminous efficacy. So we have now changed the whole of the SIU definition from measuring these quantities to defining these quantities as constants, which is very interesting. For some reason, it did not hit the news very much in 2019. So these are the units, and they are defined and interrelationships within it. It's very fascinating to think that now we know exactly what the Planck's constant is without an error bar, because that is a part of the definition of the SI units. Okay. So this lecture, now I have got the preliminaries out. I will divide it into 3 parts. The first part being the biggest, nature of the physical universe, the nature of matter, and then I will briefly discuss the origin of the universe and life. So the nature of the physical universe, So each model looks like the physical universe in a different way. We evolve with new observations, which leads to new mathematical models. But what I say is that we get deeper and deeper understanding of space-time, but must remember that the model will never be reality. It is just still a model. And what we have even today is just a model. So astronomy, when it started back in the ancient times, before we think this, the ancient man would have seen a fantastic sky without light pollution like this. Not many places on the earth will you see a sight like this. And the Egyptians had a very simple universe. The sun was born in the morning, rose across, and then was swallowed by this god in the evening. And that was their perception of what the universe was like. If you go to Sri Lanka, we have this Tisavava things where there is a huge carving 6 feet in diameter, which is quite interesting. And this has been called the Sakula Chakra, and there's been a lot of misinterpretations of this. But it basically has 7 rings in the middle. And this 7 is very interesting because 7 basically means that during those time, we only knew of 5 moving objects in the sky: the sun, moon, and the 5 planets: Mercury, Venus, Mars, Jupiter, Saturn. So those were the only moving objects. They were considered to be gods, and they moved across the fixed stars. So the 7 also are the 7 days of the week. And there are 7 rings in the center of this chakra. And what I find interesting is there is a second ring, set of 7 rings, which may indicate that we did have the concept, instant concept, that the earth was not unique in this universe, whereas all Western concepts were geocentric. So this is the geocentric or the flat earth people. I mean, this is from a book published in 1881, where this guy was a big promoter of flat earth, with Antarctica being at the rim of the earth. I have a copy of this book. It's very, very interesting. This is what, if you project the earth into the same thing, would look like. And that's what they thought. And there was a later on by people who were breaking this idea up in the 1970s, that it must be true because this model was adopted by the United Nations for their logo. But we now know that the earth is round, and that's not a theory. Anyway, so the earliest view of the universe was it was geocentric. And Aristotle had this view where the moon, Mercury, and Mars, and then the sun orbited. Mercury, Venus, and Mars show crescents, so they were close. And the other 3 planets were further than the sun and didn't show crescents. Earth was in the center. But during that same time, even though there were people who didn't have the correct idea, there were also very clear scientific observations made. And that was Aristotle. He sort of, in the 240 BC, he calculated the circumference of the earth by making precise observations and and the correct observations. He was also the chief librarian of Alexandria. He decided that the earth was spherical. And by that, he decided that he assumed that the sun was extremely far away. And from that, he managed to compute the circumference of the earth to 1.5%. I mean, that's amazing to have been done now nearly in 240 BC, which is actually the era of the Buddha's time, to have got they measured the circumference of the earth to an accuracy of 1.5%. So people, ancient times, knew on logic how to do computations and get through with the correct answer. So then came Ptolemy. He was pretty much geocentric. And he brought out a system by which he could predict the motions of the sun, moon, and planets very accurately. And then everybody thought that that was the correct view because it managed to predict to the measuring accuracy they had at the time that that was the correct answer. And therefore, that model was the one we had for 1400 years in the West. So this is a model of what the universe looked like. There was the Earth at the center. It had all the planets going around it, as I showed in the previous thing. And to correct for things like retrograde motion, and for then they put epicycles. And if it was not possible to correct it sufficiently wrong, they added another epicycle. So you had epicycles within epicycles. And if you put sufficiently large number of free parameters into the model, you can fit anything. And therefore, she was successful in predicting the motion and assumed it was correct. Now, I will come back to this. Came 1473, Copernicus came around. And in 1532, he had a much simpler model where he put the sun at the center. So that actually was a great difference because it required no more epicycles, and the star, I assumed that the stars were far away, and that model was much simpler. So that was a revolutionary thought to break some thought that was going on for 1400 years. And this is the model which we all recognize with the planets going around the sun. Tycho Brahe, now he was a positional astronomer. He didn't have a telescope, but he decided to start very accurate measurements using things like the instruments which measure angles precisely. And his observations really was the essential contribution to the scientific revolution of the time. Galileo came, he was the first physicist as such, observational astronomer. And he observed the heavens, got him into trouble with the church, but he was pretty much in the thing. Then he was an observational astronomer and observed the universe. And some of the things that were observed was Galileo's, he saw the the moons of Jupiter going around Jupiter, and he realized that there was not things just going around us, but things going around other planets as well. So that was a big break to the other people who thought that the Earth was the only center of importance. He looked at the moon, he saw craters on the moon, and broke Ptolemy's assumption that it was a perfect sphere and that the moon was more like the Earth. He saw sunspots, and that was a pretty big discovery because the sun was assumed to be a god, perfect and no blemishes, but when they saw sunspots on the moon, that broke that. And he also noticed that the sunspots rotated, and therefore from that he knew that the sun was rotating as well. And that was a very important observation. So we have Galileo making those observations. Then came the empirical theory. That was done by Kepler, and he looked at all the Tycho Brahe's detailed measurements, and he worked out 3 empirical laws, which are well understood, but he didn't know the physics behind it. He worked it out without knowing physics. He put the sun at the focus of an ellipse. He said that the radius vector sweeps out equal areas in equal times. And then he also found out a relationship between the period of revolution and the semi-major axis. Now, all these 3 things can be computed now, and the person who did it with a different set of assumptions of creating the Newtonian physics, he actually had his 3 laws of physics by which, and he put everything into a mathematical framework. So now we are going from empirical to a mathematical model. And he was able to explain what Tycho Brahe had discovered empirically. So now we have a method of being a mathematical theory for the orbits of the planets. Then, but everything was fine. Most of the measurements fitted exactly, but there were a couple of observations which we knew the measurements, but which was not exactly as Newton predicted. One of which was the precession of Mercury, or the perihelion of Mercury, was rotating about 43 arc seconds per century, a bit more than expected by Newtonian physics. And even Venus was going off by about 9 seconds per century. So everything was Newtonian physics worked most of the time, but it was not perfect. Then came Einstein. He had the special theory of general relativity in 1905, general theory of relativity in 1917. Now we are talking about just a little over 100 years ago. And general relativity resolved the discrepant observations of the precession of perihelion of Mercury, Venus and Mercury. So now we have a new theory, which is approximates the Newtonian theory for low velocities, but it solves all these other problems at high velocities. He predicted few things like gravitational lensing, which I will talk about because it is of special interest to me. And his famous equation, E equals mc squared, which was the equivalence of matter and energy, was demonstrated by the atomic bomb in 1945. So Einstein comes up with this theory, and nobody sort of understands it fully. Arthur Eddington was one of the big physicists of the time. And he says, yeah, we can check it against Newtonian physics by looking at an eclipse and seeing how stars close to the rim of the sun bend, lights get bent, and the position they will see. So they took measurements, both they predicted with Newtonian that it should be 0.87 arc seconds, and with Einstein theory, generally it would be 1.75. So there was factor 2 difference in the two. And people sent out observational teams to Africa and Brazil for the 1919 eclipse, just after First World War, got measurements which seemed to say clearly that Einstein was correct over Newtonian physics. So that was one of the first proofs of Einstein's prediction from his general relativity. Then came Zwicky in 1930s, late 30s, and he predicted that galaxies also could act as gravitational lenses. So that, unfortunately, we didn't have the technology to do those observations in the 1930s. And it was 40 years later, in 1979, that the first gravitational lens was discovered. It was two quasars which have the same spectrum and were confirmed to be actually the same object lensed and made into two. One could answer what lensing is. I mean, the simple explanation of lensing is similar to what you would see if you look at a light bulb through the bottom of a wine glass. You see multiple images. That's what the galaxy does. The galaxy works like the bottom of a wine glass and bends the light so that you get multiple images of the same object. So that was the first lens. 3 years later, they found another quasar behind a galaxy. It's extremely rare to find at these magnitudes, but it was discovered by Huckra in 1982. That was a gravitational lens, and that had 4 objects around it, which are all the same object which is behind this galaxy. I was lucky to be the first one to actually discover one of these things, or my team with the Hubble Space Telescope was the first gravitational discovered lens from the Hubble. And that was, the observations were made in 1994. The data became archival. I got hold of it. And in 95, I made the discovery, which I'm glad to have done. It was one of the high points of my career. So I got a paper and a press release, which I'm quite proud of. So let's get back to this digression to what we are talking about. Okay. 1920s. There was a famous debate about the size of the universe, scale of the universe. And that was supposed to be 1920, April 26, by Shapley and Curtis. You're talking about a time that people really didn't know whether there were external galaxies. And Harlow Shapley, who was a very famous astronomer of the time, well recognized, the authority in the field, he thought they were just nearby gas clouds. Curtis, who is not as well known, realized that, or sort of accepted the theory that all these spiral nebula are not spiral nebula, are just galaxies like our own. So there was a great debate in 1920, and each side argued its side of the story. And finally, in around the mid-20s, Edwin Hubble used a telescope to measure the distance to Andromeda Nebula and showed that it was an external galaxy. So it's interesting that it was, history of science claims that it was only 100 years ago that we discovered we were we were a galaxy on our own, and there were external galaxies. But I have a book published in 1814 on astronomy, and that very exactly describes what was supposed to have been discovered in the 1920s. So it is a very good example to say that a lot of people have logically thought out and got the correct answer, puts it forward, but is not accepted because there is no scientific proof behind or scientific observations that can justify that speculation, which you could call it a speculation, but it ends up to be the correct speculation. So I think this happens many times in the history of science, where people have got the correct idea, not accepted, and 100 years later, they get accepted. I'm sure it will be not the first time has happened. It will happen again. The plate tectonics is also another case where the person who said that all the continents can be put together and was thought of to be quite nutty was finally proven correct. So I think this is a very interesting way that science progresses, where people have ideas, they don't have proofs, they put out the ideas, then later on those ideas become reality. Okay, Hubble, one of the main things that he is well known for, and what really creates us thinking that there was a Big Bang 13.8 billion years ago, was the fact that when he observed galaxies and measured how fast they were moving away from us, and one would think, how do you do that? That is very easy, because all galaxies have a spectrum which you can observe, and there are spectral lines, and people very prominent lines, right? The calcium H and K lines. You can see those lines on most galaxies, and you can see that on the more distant galaxies, they are moved very far away, almost out of the visible range. And therefore, you can use that to compute how fast they are moving away from us. And from that, he drew this graph, and he found that velocity was proportional to the distance to the galaxy. And I'm not going into the full details, but this was a very important observation in this for us to bring to our current understanding of the universe. So his thing was that the universe was expanding and then somebody will come and say, what puts us at a special location that everything is moving away from us? No, we are just another galaxy in the universe, but it is like he had used this proportion of raisin bread analogy, that if you have a raisin bread before it is baked and it rises, or let's say all the plums were 1 centimeter away from each other, then after 1 hour of baking and the plums go 3 centimeters away from each other, same loaf of bread, but bigger now by 3 times. And then you would find that this galaxy would move away, this galaxy will move away from your observing galaxy by 3 centimeters in that duration. But the more distant galaxies would move away a lot faster. So you realize that the velocity of, you find what was similar to what was observed by Hubble, that the more distance you are away from your observing raisin in this case, the velocity of the object is moving faster. So therefore, what was 3 centimeters away has moved 9 centimeters in the same time, as well as the object which was 1 centimeter away has moved only 3 centimeters at the same time. So this is the appearance that it is the whole universe that is expanding. And that concept is quite interesting. Okay, so what is the universe? I mean, this is a concept that is very difficult to understand because you have to understand it more with mathematics. But let's look at this analogy. A circle is a 1-dimensional line, and it is a 2-dimensional object because it is on a 2-dimensional surface. It has a finite length and no boundaries. Whereas a sphere is a 2-dimensional surface, the surface of the sphere, and it is in 3 dimensions, and it has a finite area and no boundaries. That means that you walk in any direction, you don't find the end of the surface of the earth, say example. There is no corners unless you believe the earth is flat. Now, when you have to take these assumptions 1 dimension higher, and space-time becomes 3-dimensional space in 4 dimensions, the 4th dimension being time. And Einstein showed that space and time are equivalent dimensions, which has a finite volume and no boundaries. It's a concept which is very difficult for us to comprehend, how you can have a volume which has no boundaries. But that is what space-time is. Because of this, the only way you can understand it is maybe extrapolating from 1 dimensions to 2 dimensions to 3 dimensions. And then you can write it very easily mathematically, but that's what it is. It's space-time is 3-dimensional in 4 dimensions with no boundaries. So that is a concept which I think is one which is confused a lot of people, because a lot of people ask, what is beyond the edge of the universe? And there is no edge of the universe. Okay, so Einstein basically merged generality merged GRs, and astronomers observed that the volume occupied by the universe is expanding, still finite, but still remains finite in volume. So that's also a concept which is very needed, but it's very difficult to understand unless you look at this analogy or accept it mathematically. Okay, so let me not go into details of astronomy, but we have now, over the last 20 years or so, actually most of this happened over the last 10 years, where we have got a model for the universe, and it fits pretty well the observations. So we have the age of the universe now to be 13.8 billion years. I can remember a time, maybe 30 or 40 years ago, where everybody were guessing. If you look at cosmos, Carl Sagan mentions a figure of 15 billion years, because we didn't know whether it was 10 billion years or 20 billion years. So everybody used the 15 billion years, but we didn't know what the Hubble constant was. I mean, there were values. I can remember astronomers fighting with each other. When one famous astronomer thought it was 100, the other famous astronomer thought it was 50. And they used to have lots of disputes about the two values in conferences. And that was maybe even in the mid-90s. And now we know for very accurate measurements, it's about 68 kilometers per second per megaparsec, with an accuracy of about half, 0.5. Then we have another parameter which measures how much of matter that we know, which was baryon density. Like all the matter in the all the galaxies, all the stars and everything, all the interstellar matter and everything, if you add up everything, we find that it only accounts for about 5% of the universe. So that's the omega baryon density. Then we know that there is something called dark matter, which is still not understood, which accounts for about 26% of the universe. One of the things that astronomers are trying hard to identify what this dark matter is. There are many, many theories, but nothing has been finally explained. And to that extent, this term dark matter is a label to something we do not understand currently. It's something like the rotation of the perihelion of Mercury. We had the measurement, we did not know why it was. Then we have dark energy, which is, I think, a pure label. It rhymes with dark matter. And it's supposed to be almost 69% of the universe. Now, that was actually, those estimates come out pretty well with the model that we have. But dark energy is almost a factor which actually Einstein had built, called lambda, into his general relativity. He said lambda could take any value. He thought it was 0. But now we know that it is 0.69 omega lambda. And why it is, we still don't know. We don't know what dark energy is. But both have multiple theories to explain dark matter and dark energy, none which is acceptable in all respects. So we are coming to a time when we knew a lot of things, but we also have discovered that we don't know many things as well. There is also the age of decoupling, when the furthest you can see with before there were atoms to be seen, and that occurs about 378,000 years after the Big Bang. And so those are the more famous of the parameters. There are a lot more parameters that have been used in the model to model our observations. So what did I call about 378,000 years after the Big Bang? That is known as the cosmic background radiation. That is what was discovered in the 1960s, and they got a Nobel Prize for discovering the cosmic background radiation. It was thought to be noise that was coming in the TV, but finally discovered that it was actually coming from cosmic origin. It is a temperature of about 2.78 degrees, but with almost constant in all directions. And it was only recently, about 20 years ago, Kobe measured it to find small differences. And finally, about 10 years ago, we got this map of the fluctuations. And these fluctuations are like 1 part in 100,000. And this actually represents a baby picture, because you can't see beyond this distance because there were no atoms or anything. And this was the first time that we would have had atoms to look at the radiation from them. And now we got the other end. what we see out there when we look at the universe is from a sky survey, whereas we see clusters of galaxies, we see voids, we see regions where there are not many galaxies, and sort of like bubble structure of the universe. So this is what we see. And all these structures that we see now in the universe can be related back to what was quantum fluctuations back at the time of the Big Bang, and then visible slightly at the time of the we're seeing as cosmic background radiation. So if that was completely smooth with no fluctuations, we clearly could not have created galaxies and stars from it. So it was, I can remember the time they actually measured it and found out that it was about 1 part in 100,000 differences. And that said, okay, we have observed what created the galaxies we observe today. So this is the sort of cosmological view of the universe. We have the Big Bang at one end. There's something called inflation, which expanded the universe very rapidly in the first few seconds of the universe. Then we have the cosmic, after cosmic background radiation from about 378,000 years. And then we have the first stars coming about 400 million years from there. And after that expansion to see what we see now, which is if you were looking from this end, you would see the galaxies in the universe. So this is a sort of illustration, not in 3 dimensions, but in 2 dimensions of what the universe would, the history of our universe over the last 13.8 billion years. Okay. So next I will come to matter, nature of matter in the universe. That started with the old Buddhist concept of water, fire, air, and earth, apo, tejo, vayo, patavi. Everything was derived from 4 types of particles called the Mahabhuta in Buddhism. And they had supposed to have 4 derivative properties of color, smell, taste, and texture. We had in around 460 to about 400 BCE, we had Democritus, who thought about the concept of atoms, which were not geometrically divisible. So that's a very modern concept, which we didn't have for a long time. But 400 BCE, they thought about these things by pure thought logic. And he had quite a lot of ideas which have now turned out to be true after about 2000 years. And that was his early atomic theory. It goes back to the Greek time. Then you have Mendeleev, who came around in 1871. He had basically a huge number of elements which have been discovered by the scientists or very many chemists of the time, but it was a big jumble and nobody knew what it all meant, whether it was followed any logic. So he sort of wanted to teach chemistry and he thought of putting it all into some order, and he came up with the first periodic table of him, and I think that was one of the great discoveries of modern era and I think a lot of the discoveries subsequent to him wouldn't have happened unless we had a breakthrough that the elements that we observe form some sort of pattern thing. He not only used his empirical model, it was purely empirical because he didn't understand what each of these, why these elements had these properties. It was only later and now that we understand the chemistry of it. But he was very clever to predict 4 elements which had not been discovered. And he said that those 4 elements should be there because they were missing from the table that he had made for all the known elements of the time. So one of it was scandium, which was discovered in 1879, 10 years later. Gallium, which was discovered 6 years later. Now that people knew what properties they should have, it was easier for them to discover. Germanium, which was discovered in 1886. And then finally, titanium, which was discovered, was only created artificially, but had been seen in the sun spectrum, was created artificially in 1937 in the atomic reactors. So you have also another case where empirical theory goes into some predictions and then to reality. So now we have a much bigger periodic table with things. We understand all these properties, what are metals, what are, and all the different types of things. And a lot of them are now man-made as well. But it falls into a table very similar to the table that was created by Mendeleev about 150 years ago. It was the 150th anniversary in 2019. So that sort of stems from a classical structure of the atom. I'm not going to describe that. I'm sure everybody knows what the structure of the atom is. But the fact that the atom was mostly void was not known initially and was a thing. And there are lots of other famous scientists like Marie Curie who were part of the modern chemistry story. What also you discover is that atoms, one of the main things there is that atoms have different levels of electrons, energy levels. And when electrons pass from one energy level to another energy level, or can be promoted from one level to another energy level by absorption of a photon, it can give out that same energy level. And if you look at stars in the sky, we see spectral lines associated with those energy levels. And therefore, we infer that the star has those elements in the stellar atmosphere. So we can study the spectrum of stars and study what elements are there. And we know what the sun elements in the sun's atmosphere is. And this was sort of the breakthrough in a lot of astronomical study, because we could look at the stars and understand what they are. And we have now got pretty much a pretty good idea of how stars evolve. There are computer programs that can evolve stars and work out the physics of it pretty well, equations, I think the stellar. Now consider the fact that in 1880, which is just less than 150 years ago, we knew how far the sun was. We knew how much of energy the sun was producing, but we had no clue as to where this energy was coming from, because we knew that it could not be chemical. And we have to basically now well understand everything of how stars create the energy by nuclear fusion. But just 140 years ago, which is not very long time ago, in the time of our grandfathers, it was not understood. So that is, I think, what you have to consider, that science has been rapidly evolving over the last 100 or 150 years. What was true this is also, lots of, I'm not going into details about the main sequence where stars of big mass have lived very little time. We know about how big the stars should become, and most of those sizes have been computed by physics. Now we understand it fully. We know how stars evolve from being normal stars to other types, and I'm not going to go into the details, but stellar evolution is something that is very well understood. I will summarize all those graphs by saying that very massive stars, all the stars are not the same mass of the sun. The sun on this table has a mass of 1 solar mass. It has a temperature of about 6,000. It's called a G star. It has a luminosity of 1. And it lives about 12 billion years. So we are now 5 billion years after it was created. We have another 6 billion years of life. So in our cosmic time scale, we have another few months of cosmic time to live before the sun disappears. Very massive stars, which are about 25 times the mass of the sun, live only 4 million years. So they are very bright, burn at very high luminosities, and they are called O stars. And at the other extreme, a star which is half the luminosity of the sun will have a temperature of about 4,000 degrees. They are called M stars. It has about 3% of the luminosity of the sun, but would live about 700 billion years. So that is much longer than the age of the universe. So most of the stars of that type, up to about 0.75, have not evolved. The earliest stellar type stars would have been just evolving 13 billion years from the Big Bang. Okay, this is the whole story about evolution. I'm going to skip through that. And all the elements that I talked about before had to be created in either stellar evolution or subsequently. So now we not only know where the elements were created, and we know that in the Big Bang, hydrogen, helium, and a little bit of lithium was created. And so that is what happens in the Big Bang. Big Bang nuclear and fusion happened. Then we have what is marked out in green to be dying low mass stars creates a certain amount of elements of part of the element population. Merging neutron stars, exploding massive stars creates what is in things. So we have now, and then finally, these final things are created by us in our laboratory, including what I talked about, tectonium, which was only discovered, which was predicted by Mendeleev and created in 1937. So this is like where the elements come from and where they are created, which is quite interesting that we understand it fully. We also can predict what the abundance should be and what abundance we see of all these elements. And so to know, we will understand what matter is atoms level. Then we have other forces, which I'm not going into the theory. There are 4 forces of physics called the weak, strong, electromagnetic, and gravitation, which have the weak and the strong being what keeps the nucleus of an atom together. Electromagnetism is what is carried by photons, and gravitation, which was predicted, which is general relativity, which we had never observed as a graviton till only about 5 or 6 years ago, when the first gravitons were observed in with about 30 or 40 years of attempted observations. So let's look at another concept of the photon. A lot of people ask about this, so I'm including it here. What is the photon? Photon is a particle of light, but we also talk about its wavelength. So it has wave-like properties and it has particle-like properties. So a lot of people is a photon, which is a bundle of light, a particle, or a wave. It depends on your perspective of how you observe it, because a photon, in my opinion, is neither a particle nor a wave. It is an entity in a higher dimension, which can be observed depending on how you look at it in mathematics. To illustrate that, I think a very nice illustration of this is to think of what a cylinder would look like if you project it from one side. you see a circle. If you project it from another side, you see a square or a rectangle. So is it a circle or is it a rectangle? It looks very different, but it is not. It is a cylinder. So this is why I think when you look at photons with one set of equipment, it looks like a particle. When you look at a photon with some other equipment, it looks like a wave. It's neither a wave or a particle. It is both. And that's I think, a nice illustration with a cylinder to illustrate what happens to be. It depends on your perspective or thing. And I think you can use this concept in many things which look ambiguous because we are looking at it in a lower dimension. I won't go into this, but now even atom particles are sort of considered to be combination of things called quarks, which create all the particles, and leptons, which create, there are 6 types of quarks and 6 types of leptons, and 6 anti-quarks and 6 anti-leptons. So little by little, we have become smaller and smaller objects creating bigger objects, which create even bigger objects. I mean, this is the way that science has gone in. We have not gone. Somebody might come up and show that all the quarks are sort of made up of other particles as well. But we have currently understand them at the level of quarks. So this is the current standard model of elementary particles, where we have quarks and leptons creating all the particles. And to this has been added the Higgs boson, which was only discovered, must be less than 10 years. It was actually exactly about 10 years ago that we discovered the Higgs boson, which seemed to have been, which are predicted in the 1960s and took 40 years before it was discovered. And it sort of tied in a lot of the concepts. Okay, so fundamental, with all these, with the standard model, you can now, and you have SI units, you can derive a lot of fundamental constants in the universe, the gravitational constant being one of them, the electron mass, vacuum permeability E0, and a lot of other elements, particles can be measured with the currently accepted SI units. They can't be derived from the mathematical theory. So they are actually free particles, free parameters in your model. And that sort of causes a bit of problems. So the standard model is the model which brings together special relativity, quantum electrodynamics, but it does exclude general relativity. So from the 1980s, there has been many attempts to create grand unification, because people don't like 2 theories to explain the universe. One, which is general relativity, which fits very well at large distances and high velocities, and standard model of particle physics, which fits very well for small objects, quantum objects, and particles. So this has been a major problem. And from the 1980s, there have been very many physicists who spent their whole lifetime trying to create a single model. Even Albert Einstein, when he was at the Institute for Advanced Study from 1932 to 1954, he worked mostly on this thing of trying to get quantum mechanics and general relativity to be a single theory. He never achieved it in his lifetime. And people 100 years later are still trying to merge quantum mechanics, or now the standard model of particle physics, with general relativity. And what was very popular in the 1980s was something called string theory. And everybody assumed that given another 10 years or so, we would have a string theory which would explain everything. But it has not been like that. There have been many different string theories. All have their problems, all have resolved certain problems, but not all. So what we have now ended up, which is called M theory, which is a combination of all these different string theories and hoping that this combination, which will explain everything. But this is pretty much a cheat in my opinion. And I think science is in the position that Aristotle had of having epicycles and more epicycles to explain everything. It fits perfectly what you observe, but it's not reality. So I think it's time that the next Copernicus comes around, next Newton, and the next Einstein, who would finally work out grand unification. But I think we are off on the wrong direction with string theory, because it has really not served except be able to predict things without really very complicated. And as I said, whatever the theory of the universe, it should be much simpler than this. Okay, next I will talk a bit about the origin and the universe and life. It's not a subject that I know very much, but I will just introduce because it's a few concepts which I think are interesting. It starts with our concept is we assume that the Earth was young, created in 4004 BC, according to Bishop Ussher. We don't believe that now, or most of us don't believe that now. But there are people in Kentucky who think that dinosaurs walked and chased Adam and Eve out of the Garden of Eden. When you think of a young Earth, I love this book, which was published in 1822. It's a description of Hindustan, India. I have the original copy from my father's collection. It's a massive book which has a long description of the Hindu concept of astronomy. And I like these books because these are untainted by current understandings. And you know, this is the understanding of the Hindus during that time. And this particular book has a one quote, which my father pointed out to me. It said, a learned Brahmin laughed on being told that we Europeans reckon only about 6,000 years since creation of the world, and pointing to an old man with a long white beard, asked if it was possible to believe that he was born by the preceding day. I mean, this guy firmly believed in the 6,000 years. The science also accepted the 6,000 year Earth at that time, but it was considered much older. Very interestingly, they have a concept called the Day of Brahma, which works out to be 7.5 billion years, which is about half the age of the universe. So to get up to that order of magnitude, I think is quite amazing. Then Charles Darwin came with the origin of species. We didn't know how it worked. Survival of the fittest is how he explained it. And in 1953, by understanding how the DNA works and how it is encoded, we have much better understanding. I'm not going to theory of this. I know nothing about this subject. But basically, everything can be understood by 4 DNA chemicals which create the bases of the DNA. Now we talk about a more physics as problem that comes around by this, is that I told you about SI units. So what you measure or the number you get, unlike if you say pi is a number, it does not depend on what it's a dimensionless quantity, which does not depend on what parameter SI units are defined on. But you can also define certain other dimensionless quantities by dividing certain constants. Now here in this equation, which is for the fine structure constant, you have E, which is now a constant, H and C, which are all constants, and it's basically a measure of permeability, E0. Now we find that that value from the observations is 137.0359999084. At one time, scientists thought it was exactly 137, but that didn't pan out. Now we know, and we have practically got a measurement to be this number. So we know it is correct. But we have a problem here. That is because we know that if that number is different by about 4%, which is a variation which is not very much, there will be far less carbon and oxygen created in the universe by stars. And it has sort of got a lot of people asking, how is the universe so fine-tuned to have a fine structure constant so accurately defined to 4%? And if it was, why wasn't it much larger? In which case we wouldn't have what we have now. So who made it so exactly 4%? Now that is a thing that has been used by many people for the existence of a creator God or intelligent designer, saying he is the one who chose the value of the fine structure constant. Now, I don't like this creator universe thing. I mean, one of the best movies that gave that concept is the movie Matrix, where he made us universe to be a simulator of some other larger being. But was our universe just a matrix-like simulation? And I will argue that if that is the case, and we have a God who created it, then everything like astrology, which I fight against, could be irrational, but it could be built into the simulation. But my fundamental question is that if some intelligent people were making a simulation, why would that God create an enormous space-time for just this tiny flash in which all human created myths and religions exist? So as I showed right in the beginning of this lecture, we occupy a tiny bit of space-time, minute region of the universe, for a fraction, a couple of cosmic seconds, and practically a flash. But if this whole universe was a creation, a simulation, it sounds really logical for anybody to create a simulation so large for such a small bit of space-time. So astronomers don't like that idea. So what they do is they think that our universe is just one of a large number of universes in a multiverse. So the concept of a universe is a single universe. And now you bring the concept of a multiverse, which means that we are just one universe in a multiverse, which is at a higher dimension. Now, multiverse is a higher dimensional thing and interact with each other. And each would have different fundamental constants. So there is now no problem, because now you bring the idea that we are the Big Bang created one of those multiple universes, which is where we live in. And each of those multiple universes would have different fundamental constants, would have the whole infinity of them if you wanted. And only in a universe which the parameters allow the evolution of stars and to make heavy elements during and have a lifetime, during its lifetime and death, can you create chemical evolution of life. And therefore, so this concept of anthropic principle saying we exist, so our universe has to be a universe in which the fundamental constants are conducive to the chemical evolution of life. So you talk, this problem of having a fine-tuned fine structure constant is explained by having multiple universes and using the anthropic principle to say, we exist, so we have to be in one of those universes which had the fundamental constants which created stars and galaxies and created the chemical evolution of life. So this anthropic principle is a fundamental way that astrophysicists and scientists get around not have to postulate God. Science, so now let's look at what science said. We have science, age of the universe been 13.8 billion years. The sun and earth formed 4.6 billion years ago. The earth took about 500 million years to cool and to allow liquid water. We know that the earth was not hospitable for creation of life for about 500 million years. But we know that cellular life forms have been formed on Earth 3.8 billion years ago. So life originated on Earth in about 250 million years, or about one orbit around the galaxy. Now we have another problem, which is that how did life origin, chemical evolution of life happen in just 250 million years? So we don't have a theoretical postulates to compute the probabilities of chemical evolution of life. We don't know how many stars have planets. We have known that most of the stars have planets and many have habitable planets like ours around them. But we have still not detected any signs of life. That is not surprising because the first exoplanet was confirmed only in 1995, just 25 years ago. So we have actually hoping that we might find evidence of life with the new telescope, the James Webb Space Telescope that was launched successfully, that is in orbit, because that might give us infrared observations to detect life in other planets or solar systems. Then we have, that is a NASA, ESA, and a Canadian Space Astronomy Project. Right, all life on Earth has, now the next problem is that we know that all life on Earth has a common origin, and that origin was created in about 250 million years. And then, okay, now we have, you can start with the scientists, and if 250 million years is argued to be not enough to create a chemical evolution of life, we can use all habitable planets in our galaxy or the whole universe to get as large a multiplicative factor as needed. So this is another use of the anthropic principle again, because we then say the soup or the chemical soup that created life was existing in many planets in the universe, in many solar systems, but the chemical evolution of life happened on Earth, and we know it happened on Earth because we are there and we exist there and we observe it. We are there to observe. In all other places or solar systems where there is no life, those solar systems will not have life to observe it. So we have used the anthropic principle twice in this exercise to overcome two major problems of creation and the postulate of God. So I will end my thing now. I've taken too much time, but basically I want to say is that in 1880s, just 150 million we knew the distance to the sun, we knew how it happened, but we didn't know how it produced it. Now we understand it fully. Charles Darwin recognized evolution and had no clue on how it was encoded. Now we understand a bit more. We understand DNA and the genetic code, which is under study. So in conclusion, I will say there are a lot of observables like dark matter and dark energy, which we don't understand at all in our current scientific model. We have only started investigating biological stuff like life and consciousness. We don't understand it very much. But considering the fact that in a 4,000-year civilization, or 6,000-year civilization, we have done most of these breakthrough discoveries in the last 150 years. Unless humans destroy progress of science with a nuclear war or whatever, we can hope that the greatest discoveries are yet to come. So I will conclude with that. And sorry for taking about more than an hour for this lecture. And I will now stop there and stop sharing and open it for questions. Okay, if you excuse me for a second, I'll be back in a second. Hi.
Right. Thank you very much, Kavan. And that was really wonderful. I was actually, I wanted to go and get a cup of tea, but I couldn't stand up to, miss whatever the section you're on. So I stayed all over. Right. Anybody waiting? I can't see any hands. Kavan, if you can help me with this, can you see any hands?
Udita has put his hand up.
Udita, okay.
Hand up.
Yeah, I was expecting Udita's question. Go on, Udita. It's your turn.
Hi, Kavan. Thank you very much for your talk. I was looking forward for it, and certainly it was interesting as I thought. You touched on some of something which I have been sort of arguing for some time. But before that, I just wanted to give you some facts which you may recognize and you may know. Can you hear me?
Yes, I can hear you.
Yeah. Okay. So the one thing is the fine-tuning argument.
Yes.
Now there is I don't know whether you mentioned, probably you didn't mention I'm going to quote you two figures. Okay. One is the matter to antimatter ratio,
yes,
which is 30 million to 30 million and 1.
Right.
That ratio, one ratio out of 30 million, right, is the reason why the universe is existing. Do you agree with that?
Yes.
The matter to antimatter ratio.
What happened at?
Yeah, I just want to give you a few other things. Then Stephen Hawking had said that the critical density of the universe is so finely tuned, it is 1 into 10 into the power minus 60.
Okay.
Right? Yeah. Okay. So now that is what Stephen Hawking said. And Carl Sagan's equation predicted that, if I'm not mistaken, that in the universe there are 10 into the power 24 stars are there, and out of that, according to Carl Sagan's prediction, then there should be life in 10 into the power 21 stars.
1 in 1,000. We have much better numbers now that we know.
Yeah. Okay. So I don't know whether you know about Borel's law. Do you know anything about Borel's law?
What is it? No, remind me.
Borel's law is, it says that anything under the 10 into the minus 50 possibility cannot happen as a random occurrence in the universe. So anything less than 10 into the power minus 50 cannot happen as a random occurrence. Now, according to the Stephen Hawking's calculation, critical density is 10 billion times less than that. Okay. So it comes to the argument of fine tuning. Now, the other thing is why only there's life on Earth.
Okay.
Now, according to the factors needed for life, why Carl Sagan got it wrong was he predicted that there could be life in a Goldilocks zone if there's a sun and if there are planets at a certain distance, then those planets will have life. But today we know that there are more than 200 factors needed for life. And the
Yes.
chances of those 200 factors happening in any place is 10 into the power minus 99, which all means that they are more than the Borel's law.
I mean, I don't know what basis Borel's law is. I mean, the point is with anthropic principle, that number can be infinity, because the most unexpected, because for example, I can look at all the planets all possible habitable planets in the universe, right? And since we do not know whether there is life in other parts of the universe, and the life is only on Earth, then I can make that factor as large as possible. Now, if we find life on Europa, for example, which is supposed to be very much something that could have life, Arthur C. Clarke talked about it. I saw a recent paper saying there is a lot of possibilities that life may exist on Europa, which is the moon of Saturn. But if that life is similar to the life on Earth, then we could think of to be contamination. Life originated on Earth and contaminated Europa over the billions of years. Now, that is not going to be surprising. Now, on Earth, as far as I know, all life go down to a single evolution, chemical evolution. There was one chemical evolution, and all life is related to that single chemical evolution point, right? So if we find that the Europa life is also have that same signature or evolved from it, then we would consider it independent. But now if you find Europa life is completely independent, then we are getting to a bit of a problem, because that factor that I thought of putting cannot be put in, because we know that chemical evolution independently happened in two places. Now, if you find life in a nearby star, then also is a problem, because then we can count how many stars there are within that radius, how many stars and how many planets there are, and that factor cannot be bigger than that. So I think we really don't know very much, and we are really in a position similar to what we were in 1880, when we knew exactly how much of energy the sun was producing. We knew it could be chemical energy, and we think so. Maybe evolution of life is also something like that, which we do not understand. It may happen but you cannot bring an intelligent design into it, because then you can always ask the question, who made that intelligent design? Right? You cannot you can just step it back one step and say, so God created, then I can ask the question, who created God? Right? So that is no solution to the answer. So the anthropic principle basically is the solution. Double use of the anthropic principle is the only logical solution to this answer. I'm not sure about the big factors you're talking about, but with the anthropic principle, I can make that factor as big as possible.
What I'm saying is, as far as we know, the fine-tuning of the universe and life has to be explained. It is beyond, as per Borel's law.
You're quoting Borel's law like you're quoting God created the universe. I don't know what the Borel's law and why that is. Can you explain to me Borel's law? If you cannot, please do that.
So Borel's law is anything less than.
Yeah, but you're just stating what.
No, that's a law.
What is the logic behind that law?
No, that's a law that is not what I have created,
No,
but
you,
but it is established law.
I can make an arbitrary statement saying it's 10 to the minus 50 or 10 to the, you cannot make a law there is nothing called a law like that. You have to justify the argument from basic principles. You can't come up with a magic number like Borel's law. I have not understood. I don't remember what Hawkins said and how he got a number and what that number and what it implies, but there's a lot of misquotation of what Hawkins said by a lot of people who take a number from Hawkins and quote it in a different way. But please explain, maybe you can give us a lecture at this and explain to this in a logical way how that, what, you can't bring a law. It's like saying God created the universe. You cannot.
No, I haven't brought the law. It is an established law.
No, there is nothing called an established law. There's only established law in parliament, which are idiotic. There is no established law in science. There is nothing which is sacred. There is no gospel in science. You can't establish saying this is the law. There is nothing sacred in things, and you can't quote it saying there is a Borel's law and therefore nothing. Therefore God exists. There is nothing like that in science. Science does not have laws.
Well,
even if you read it in a book, that science does not have laws.
Well, you can read about Borel's law.
I don't. I mean, if you explain it to me, if you can explain it.
No, it is not something I have created. I have imagined. It is.
I have read in the book that God created the universe in 6 days. That does not make it a fact. I have the book, in fact, which says gives the 4004 BC date for the creation of the universe on October 21st. That does not make it real, right? Just because it's published in a book or published by somebody. I mean, Usher told that the earth was created in 4004 BC does not make it reality. I don't know who Borel is. He's not a very famous person, and you are quoting somebody who I don't know. So you can explain to me what the logic behind Borel's law is. If not, it is meaningless.
Well,
do you understand the reason for that law?
Sorry?
Do you understand the logic behind that law?
I don't know the logic behind the law, but that is a well-established
law. You cannot quote something that you do not understand. The Buddha also said, please accept things that you understand. Don't speak about things that you don't understand because you can misrepresent them. And since I don't understand what you're talking about, shall we go on?
Yeah, I think we'll have to conclude there, but you can have a look at Borel's law and what it means.
Can you send me a reference? I will look at.
Sure, I'll send that to you.
Okay.
Okay.
There's another hand up.
Yes, whose hand is up? Oh, Kirti D. It's your turn, Kirti?
Please unmute. Okay.
Hi. I'm sorry, my phone is ringing, so I'm trying to stop the phone.
Oh, you got a nice background.
Well, I'm in the universe. No, I'm not going to ask you about the life or the God or anything like that.
Okay.
I'm going to ask you something very simple, much more simple, hopefully.
Okay.
Now, you mentioned a book written in 1822 by some Indian author.
Yes.
And that had some facts. There was no evidence to prove them.
What?
As you said, that book contained some information.
Yes.
But at the time, they couldn't prove them. But later on.
Right.
So my question is this: is it possible that the ancient Indians had a lot more knowledge? But wait for my second question.
They may have looked at the universe in a different way. I mean, the Greeks looked at the universe in a completely different way than the way that we're looking at the universe. And they worked out of things, right?
Let me ask my second question before you answer that.
Okay.
My second question is it possible that the humans had a lot more knowledge a couple of hundred or couple of thousand years ago because of an atomic bomb or something like that? Because the world is moving in that direction. When the intelligence gets bigger and bigger, we develop atomic bombs. One atomic bomb is enough to destroy the whole world. We'll have to go back 1,000 years to come back again.
Unfortunately, we know the history of the Earth much better, because you can take core samples of thing and you can go back millions of years by knowing what the atmosphere was.
I fully agree with you, but
so we know the history of Earth pretty well to tell that there was no other civilization in the ancient times.
No. Let me come back. There is evidence that there are lots of underwater cities under the sea going back several thousand years.
Yeah.
And also I'm aware of that in northern India, there's a crater which they believe could have happened due to an atomic bomb. There is no proof.
I think it would keep signature at sort of signatures which can be investigated to discount that sort of von Däniken type of theories. Von Däniken was very clever and created all these different theories about ancient life forms, ancient civilization, people who aliens who visited us. I think all of those are very interesting, but I don't think they have a reality which has been proven now.
No,
I think
I appreciate your answer and thank you very much indeed. I want to ask a very hypothetical question now.
Okay.
The way the world is moving today, in the last few days, if we had an atomic bomb in the next week or next couple of weeks, would we be left to have this debate anymore for another few hundred years?
Yeah, that is one of the reasons why we are trying to go to moon and Mars, so that we are not.
But if they use atomic weapons in the next few months, we wouldn't have enough time to go to anywhere.
I agree, and that is one of the. Hopefully, we won't go into nuclear war. But remember that about 70,000 years ago, right? There was time where if you do the genetic DNA analysis, they find that about 70,000 years ago, there were only about 1,000 humans in the world. 1,000 what they call mating pairs in the world, which means a population of about 2,000 people from whom all of us are descended. So the Earth has gone through crisis. Okay. Look at the old things, crises on Earth. I mean, we are just the couple of cosmic seconds, as I said. We had the dinosaurs getting wiped out who had been on Earth for about 200 or 300 million years, right? They got wiped out by one asteroid hitting the Earth, right? And if that asteroid didn't hit the Earth, most probably the dinosaurs would have been still living around here, and we wouldn't have been there because the mammals wouldn't have evolved, and humans wouldn't have evolved, right? That is a nice accident. Maybe the humans will get wiped out, and something much more intelligent than us will take over. Maybe. But I think atomic warfare might kill humankind, but will unlikely to kill life on Earth.
No, that's very true. I will agree that if you are wiped out,
yeah, we can get
something will evolve. But the thing is, unfortunately, our children and grandchildren would have no place to discuss these things.
Unfortunately, I think that is one of the reasons, which is the major justification that humans should go outside the Earth and colonize Mars, so that if by stupid nonsense we destroy ourselves, that's why I ended, and that's what even Carl Sagan says, what we do in the next cosmic second is very important for the survival of humans on Earth.
So thank you very much indeed. I can see a few other hands are up. Thank you.
Thank you very much. And let's go to Tiger then.
Hi, Jaika.
Hello. Thanks, Kavan. That was a fantastic talk, very enlightening. Just a few questions and an observation, actually. I jotted it down. The observation first, about those 4 elements that you said the Buddhist had made a concept about.
Yeah.
I think,
When
am I right in saying that they were probably pre-Buddhist? That Buddhist.
Buddhist, the Greeks also had it.
Yeah, and I think that was, if I'm right, they are sort of empirical, more sort of by their own perceptions of the world around us.
I won't call it, I don't call it Buddhist. I call it sort of the most ancient
Yeah.
concept of the 4 elements, Apo, Tejo, Vayu, Patavi. Those are the Buddhist terms, but clearly the Greeks also talked about the 4 elements.
Yeah, and I'm sure I have read it in some way in Hinduism as well, that sort. So that is one. That's just the observation. Then my question is, I mean, we are talking about carbon, hydrogen, oxygen, life forms on Earth.
Yes, yes.
Now, all right, and we are talking about this sort of Goldilocks zone in which life similar to ours could form. Could there be life form, or maybe even intelligent life in the end, in other chemical and other?
Maybe they are talking about silicon life and various
Yeah,
things.
that's right.
We are biased, but one of the things is that if you take the abundance of these elements, right? If you want chemical evolution, you need to have a large abundance. So the carbon, oxygen, nitrogen is the most abundant of the elements. So if you go further down the periodic table, they become less abundant, and therefore the probabilities of chemical evolution become less.
Yeah.
So the chances are that if there was chemical evolution as we understand it, then if you want to have, you do need to have something like a DNA. I wouldn't say that it has to be a DNA, but it has to be able to store knowledge, to record it for the next generation to come around, right? Yeah. So you need some process. I don't think the DNA is the only solution, and those 4 base pairs that which all our DNA is based on, is the only chemicals that can do it. I'm sure there is much more variety of chemicals which might create a DNA, like a recording device to give inheritance. I would think that is more logical and possible than thinking of other elements. I mean, look at those 4 chemicals. They are sort of pretty complicated structures, right? They work, and we know our DNA is created with those 4 things. But I wouldn't be surprised that there are no other solutions.
The reason why I asked that question, Kavan, is you like science fiction, sort of intelligent science fiction, which has some scientific basis.
Yeah.
I read this fantastic book, but the story was so fascinating, but I can't remember the author's name. And in fact, Arthur C. Clarke has commented about it as well, that he wished that he had written it. Okay. It's called The Dragon's Egg. It's about life forms evolving in very high temperatures, close to a sort of very hot sun.
Yeah. I mean,
at different temperatures, could these chemicals behave differently?
We know on Earth that there is life existing at the sort of bottom of the ocean, where the only energy is coming not from the sun, but by geothermal energy coming from the ground and the volcanic vents. And there are sort of a lot of, and in fact, most of the theories about chemical evolution of life on Earth thinks that life actually originated in the geothermal vents. So I think life has been observed in extreme conditions. So I think people are surprised to see where life has been found. So I think the Goldilocks zone as such that is defined for our life that basically a region of the solar system where we can live is what we call the Goldilocks zone. I'm sure there may be life on other parts of the solar system, which we don't still know whether they do exist or not, but which are much more extreme, because even on Earth, we have found life in extreme conditions. I mean, much more extreme than one would have predicted 100 years ago.
Yeah. Thank you very much. I mean, that's brilliant. Thank you. Thank you for the talk.
Thank you.
Okay, let's go to Mahendra.
Mute myself. Yes, mine is a much more mundane reflection, really. When I listened to you, I realized that people who are not mathematicians, who are not physicists, have hardly any chance of really understanding what is going on, and we had to accept what's said by the experts. So in a way, we break scientific theory in ourselves by accepting what people say without actually looking for the evidence. The evidence is that the expert said so. I mean, if you ask me, do I believe in some of the theory, I can say, well, it doesn't make sense to me, but the physicists and mathematicians, it makes sense, so therefore I accept it. That's just a general comment. My comment is, I know that as human beings, we are curious, and we like to know, we like to understand, and so we'll go on trying to figure out things. But as a result of the great understanding of matters that you referred to, how has humankind benefited? Have you seen any tangible benefits for ordinary human beings on this planet as a result of knowing some of the answers to the deeper questions, or pursuing, at least trying to pursue answers? That's one. The second point is just not that you said so, but it's a common misunderstanding that evolution is Darwin's theory. It's not. Evolution has been there long before Darwin, but Darwin is the first person who actually gave a very proper, scientifically analyzed explanation without really knowing anything about genes, but he gave a very tangible evidence of why he believes that it could happen. But Darwin is not the person who designed evolution. He's the first person who came with the theory of natural selection. Okay.
I think with respect to the problem, I think for somebody who knows no science at all, or doesn't have, O-level science background, then you have to accept thing as no different to a religion, right? I mean, because you are told things and you have to accept it. Hopefully, we should overcome that by giving everybody at least O-level science education, so that they have some ability to at least understand the concepts of science. And what I was trying to do was, without going in through the details of science, actually give it the overall framework of how the science decides things. But I think, unfortunately, a large proportion of Sri Lankan population, including a larger percentage of politicians in this country, don't understand science at all. And therefore, we have suffered the consequences of that lack of understanding. If you take what benefits science has given, I mean, your cell phone is one of the biggest benefits. And that may be not only to you, but to even beggars now have cell phones, which they use. So I think that is become universal. And that.
Sorry, Kavan, I'm not talking of benefits of science. I think you can.
No. I tell you the cell phone was created by the micro miniaturization that was required to send man to the moon. Right? When people work in creating certain things to achieve very complex tasks, the byproducts of those endeavors trickle down to the general population for much more useful things. Your non-stick saucepan also is a direct product of the space exploration of producing material which was needed for space exploration. There is enormous amount of stuff which after 10 years or 20 years of being developed here, I mean, most of the medical instruments that have been used for things even the X-ray machine stemmed from basic fundamental understanding of what X-rays are and the discovery of pure abstract research done by Marie Curie and all of them. There was no, and at that time, they didn't know whether this was going to be any use at anything. But now we can't live without it. So you can't, I think basic science research is required. Now, cosmology, on the other hand, is a bit more abstract and it's unlikely to come into practical usage, whether we know how the universe works. But I think it stems from a basic understanding that maybe at some point we keep on asking, and we've been telling God created the earth, and therefore we don't have to talk about anything else. Whereas by understanding how the universe actually operates on a very large scale, we are answering these same age-old questions in a more logical and mathematical, hopefully, mathematical so far with respect to the physical sciences, not so mathematical with respect to the biological sciences, but it is actually coming there with the DNA. We are getting sort of much more mathematical theories which will come. It's not all there, but most probably in 100 years' time, we may have a standard model of the DNA, like we have a standard model of how, and then we might understand more about how evolution happens. I don't know, but I think without basic research, which does not immediately show promise or usefulness, we will never go beyond getting into the progresses in science. And that's what they did for 1,400 years of Aristotle. They accepted Aristotle, agreed with what he could predict the motion of the planets, and they were happy with it. And there was no progress in our understanding. Those 1,400 years did not produce a cell phone or non-stick saucepan. But the last 500 years, with our progress into science, fundamental research, we have got the cell phone and we have non-stick saucepans.
Thank you. I agree with you. But for me, the most important message in science, which I tell people whom I know, is the humility of science. Science doesn't claim to know the truth. Science says we can explain the phenomena that we observe by certain theories, which can in the future be proved to be wrong if new facts emerge. And that's great. That's humble. That's humility.
I don't think we'll ever know the truth. We will get, as I started, we will get closer and closer to the truth. But whatever model we have of the universe will never be reality.
Well, I'm actually contrasting with religion, which says they know the truth, where science says we don't know the truth. We are trying to explain phenomena by giving certain theories. Which
some of the people who talk against
science never talks about absolute truth. That's what interests me.
Right, and I will tell you, a lot of the people who argue between science and religion say science is changing all the time. You said this on one day, you said this was good on another day. This is not constant, whereas in religion, we have got a consistent message. And I keep telling them that is what science is about. We are a dynamically progressing knowledge base, unlike religion, which is gospel. Okay.
Thank you.
Thank you very much. I got a question. I'm not seeing any hands up, so I will probably a comment and a question. To start with my comment, well, I can understand people using science as the ultimate truth, but science itself is changing. And I just had a look at this Borel's law on Wiki, and it says Borel introduced it in a book written for non-scientists as an example of the kind of logic that any scientist might use to generate estimate of the minimum probability. And it's not a validated scientific law for anything. Anyway, we can forget about that. But in a world where people tend to use what's appearing in WhatsApp as the gospel truth, it's no wonder we are hearing these kind of laws coming in. Anyway, moving on to my question. I've heard, there's this about the Big Bang Theory, and I've heard that some recent discoveries challenge the Big Bang Theory because the matter is not dispersed universally. So it looks like there are some massive empty spaces which is against the Big Bang theory, which according
that was a problem that was there about maybe 30 years ago, and you may have read a book which was written around 30 years ago, before the cosmic background radiation was detected, and the flux, because at that time cosmic background radiation could be measured only as a constant. Everywhere we looked, we found the same constant. We could not measure the fluctuations. Hobie, which was one of the earliest things to measure, showed there was some fluctuation, but it was hidden in the noise. And then finally, now we have the Planck mission of 2015, where it had the resolution. These were dedicated telescopes which were sent to space for the dedicated task of measuring the cosmic background radiation to a precision where we could start using it. So now those observations have been processed through the models. And so that problem, as you talk, it matches. And in fact, that's what we are using. We see huge voids in the universe created by the cosmic fluctuations of that we see in the cosmic background radiation. And that is why we can derive all these parameters, because we use the distribution and the Fourier transform of that distribution and match it up against what we see observationally, and that we derive a lot of the parameters. So I think that is an old problem which has been resolved over the last 20 years or so.
Okay. Thank you very much. And a subsidiary question to that. So in the past, there were 3 possible outcomes for the universe. It's predicted. One is eternally expanding universe. One is expanding and contraction, and the other one is a stable universe. So which is the current thinking at the moment?
Current observations tend to say that we are not only expanding, that the expansion is accelerating. So it is a sort of, and that is what brought this dark energy story, that there is dark energy which is expanding the acceleration. And that is all built in and now built into the model, but the model sort of, when you fit in with the constant called lambda, which is what I showed, which required us to have 69% dark energy of everything in the universe, and the baryonic matter is just 5% and dark matter is 26%. Now, that sort of universe, and what we are observing is that it will expand forever. And then finally, it will expand to a state where it will be absolutely nothing. All the stars would have died, all the galaxies would be dead, and there would be absolutely nothing in a couple of trillion years. Now, some of this is, I don't think it's absolute truth. I think that is the current model. And I wouldn't be totally surprised if in another 10 or 20 years, observations become better. The model we know that the model has to improve because we have certain things that we don't understand. We need a grand unification. Once the model improves and we have a better grand unified model and a model which fits more of the observations, and we understand dark energy and dark matter, then things might change. There may be major changes. I mean, who knows? There may be a major change as much as Copernicus brought around. I mean, who knows? And I think you have to keep an open mind on that. Maybe we will go to a time where we understand life and consciousness as a higher dimension of space and time. There may be an Einstein in the future who merges the biological universe with space and time. Who knows? I think we have, at some level, we have to say we don't know. And I think that is where maybe certain religion comes in. But I would talk against astrology very strongly, because unless it is not what I call space-time invariant, because astrology is geocentric, and we know that everything that is geocentric does not work. And we know that the universe is space-time invariant. So there are certain observations now which we didn't know 100 years ago. And within those observations, there's a lot of things that we don't know, we have to live with till we get to know them. And hopefully we will get to know them before we destroy our civilization or leave it to the next civilization to carry it further, or not actually start from scratch and carry it further without destroying themselves.
Thank you very much, Kavan. I'm looking for any other hands. Are there any other questions anybody want to ask?
I wanted to show something.
Please do.
How many have seen this? I thought this was a nice toy. I bought it 2 years ago. That is the periodic table.
Yeah.
And it has 83 elements, all except the radioactive elements, embedded in small little boxes, corresponding boxes,
The real elements.
including the gases which have been put inside little plastic bubbles.
Can I have the gold bit, please, and the platinum?
Yeah, all the everything. Those are common compared to some of the other stuff that is in this 83 elements. So
Right.
they only didn't put the radioactive stuff because but I think uranium is there.
Where did you get it from?
It was for sale in the US, and I decided it was such a clever thing that I will buy it. It was, I don't know whether they're still available, but I thought that was a nice little toy I got about. It was actually produced for the 150th anniversary of Mendeleev table, and I think that is a nice thing that
Yeah.
Right.
I can see Mahendra's hand up.
Right. Just to say something, this might sound like something in support of Udita, but I do believe his sincerity. And this is to say that from a scientific point of view, if you examine the question of God, you can say that there is no proof of any viable proof, acceptable proof for the existence of God. And there's no need to postulate the existence of God to explain the universe. So that's might be my scientific position. In other words, I'm fairly agnostic. I think there is no proof, and there's no need to bring God to prove things. Udita is trying very hard, not in a silly way, but in quote scientific way of trying to show that there is evidence for a creator. Now, I don't agree with him, but that is better than people who just say the Bible says so, or the script says so, whatever. So Udita is trying hard to put his viewpoint, but using science as a medium. So
I believe in a personal God. I think. I mean, I don't believe, but I think that people need a personal God, and the people who believe in a personal God, right? It's completely personal, not a physical God. Something that they believe in helps them a lot. And I know people who would have gained to get strength of courage in times of sorrow by the belief in God. So I don't think it is up to rationality so anybody to say that God does not exist. I only saying that God does not exist physically. I know astrologers who believed astrology who are supposed to have died on the day that they predicted they will die. How did they die that day? It was not that astrology was true, but they believed in this so much. So I think one has to accept the fact that there is certain things that we don't understand in science. And one of which is that the brain has power over our body. And that is what that silly question I asked at the last meeting was, that whether the queen willed herself to live till she met with the new prime minister, and then her responsibilities was over, and then she died. I mean, I think that I know my mother wanted to live till her daughter got a baby, and then she felt her responsibilities are over, and 3 months later she died. So I think there is a lot of that which we don't understand, how that works, how you can so will yourself to live or die. I think if you are sick and in hospital paralyzed, whether you live or die may not be not only the medicine, but whether you want to live and whether you have the will to live. And I think that those things we don't understand. And I think there is a lot of that. And that will to live might come with the belief in God or astrology or whatever. And for that reason, I think we cannot discount those things having mentally effects on you, which are not within the realm of science. But that is all not physical, not a physical God, not a physical God that creates the universe, but which influences you by your own thought process. That's my acceptance of what it must be.
This reminds me of the famous Pascal's wager as well. Have you heard of that one, Kavan?
Yeah.
Pascal's wager. What Pascal was supposed to have been arguing was, okay, there could be a God and there's no God. Those are the two options. So if there is no God, then being a non-believer is not a problem because I won't lose anything. But if there is a God by any chance, I wouldn't dare to be on the wrong side of him. So therefore, I would be a believer. So let the people who want to believe use Pascal's wager.
I have no problem with that, as long as they make sure that they don't get exploited by others. Because immediately you are a believer, you get exploited. There are people in this country I know who personally have told people I have known, you give me all your money, give me all your savings, and we will look after you for life, right? So, and there are people who have done that, given up everything they have, assuming that the other person is going to look after you for life. And you get exploited. And if you take the people who get exploited by doing puja and various things, and the country also has suffered by it, by this sort of belief. And I think that is the logical problem. If it is always positive reinforcement of thing, if because of belief in God, all the politicians decide not to be corrupt, that would be fantastic. But unfortunately, politicians think that they can pray to God and get around all the corruption they do. So that is not positive. But if it is always positive, I have no problem with the concept of God or astrology or anything.
I can see Yanis, but he is not going to ask a question today. Yanis, you want to say something or ask something? No? You usually go for such questions. You're on mute. Yanis, you're muted still.
Right. No, I am a firm believer of the Confucius theory, which says it is better to be thought of as a fool and remain silent than to open your mouth and leave no one in doubt. So I'm a firm believer of that. So I have listened to it very patiently, absorbed what has been said, and I think it's an hour and a half well spent.
Thank you.
Thank you to the speaker.
Any other comments or any other questions? If
Sarah,
not,
you all the way from Court's time.
May I say something, Kavan? Please.
yeah, please, Priya.
It's the question of understanding the dark matter. And I understand perfectly well with abstract mathematics leading to the physics part of it, but I don't understand the physics. So it's the physics that has let us down in understanding the dark matter. Is that correct to assume that?
Yeah, we have, let's say we have a model. We have the model has Einstein's the lambda, which is the one that gives dark energy. Dark matter is something different. We know that the rotation curves of galaxies are constant. We know how to compute what the rotation curve should be if it was all the matter inside. We see a lot more matter. So we have two concepts which require dark matter and dark energy. or what is labeled dark matter and dark energy. There have been speculations whether that is a result of interactions with other universes in the multiverse. There are hundreds of speculations in different directions, right? I think, in fact, one of the speculations was by a Sri Lankan lady.
Yes, lady science. Yes, I remember.
She did a lot of speculation that way, and I think we should have lots of different ideas coming in, and one of the 1,000 or so might turn out to be the right answer. If we don't think in all the funny and look mad ways, we won't come to the right answer. I am reminded of this by what the head of Sun Microsystems, he came to Carnegie Mellon and gave a symposium. He said in the 1960s, to get a grant proposal, you only had to be 3% possibility of it being successful. He said in the 1990s, to get a grant proposal, you had to be at least 30% possibility of being successful before you were given the grant. Now, he said at 3%, you will have fantastic major breakthroughs in science, but at 30%, you will only have extension of what you already know, and you will not have that breakthrough which came from a completely unknown direction. You almost have to be able to prove that what you are asking money to do is doable. And that does not help to get breakthroughs, because you have to explore the unknown. And the complete unknown, you will never get a grant money to do unless you are rich enough to do it yourself. So I think this is the problem, that most of what we have today, even the cell phone, stems from research that was done in the 60s and developed over the next 50 years. And we are not investing at the level, and that's why projects like Artemis, I mean, we went to the moon 50 years ago. We are hardly getting off the ground now. 50 years later, trying to go back to the moon, and we are sort of postponing. Why? We did it in 1969. Why can't we do it now? Basically because the funding is at a level which does not, and we have lost all that knowledge of a lot of people over the years. And that is the state. I think we need to, that is why the advantage of us accepting funding a major project like going to Mars will work, not only for the benefits, but for producing technology that would be of use for humankind.
Yeah. Thank you.
Take also the tokamak, right? The fusion energy. I can remember in 1970, it was a done deal. In 30 years' time, we will have fusion energy, right? This is the 50 years' time we don't have fusion energy. And if you ask anybody now when we will have fusion energy, they will say in a 30 years' time. That is basically, you can't predict breakthroughs, but the number of breakthroughs depend on the level of funding. And I think the level of funding, because is much lower now than in the 60s. And the 60s funding was because there was a politically motivated. They were running a race with the Russians. So they opened all the books. But my belief is that if they take the $700 billion a year that they use to fund the Army and the Air Force in America and use that to go to Mars and stop using that to have fights with every other country, we will progress much more rapidly.
Yeah, you have a point. Thank you.
Kavan, we have a question from Sam. He's here in this forum, but looks like he's out gazing at the universe and using his Samsung Galaxy to join our program. His question, as far as I can read, is there an astronomical or scientific way to define consciousness? I think I changed the wording a little bit, but that's hopefully is what he wants.
That I think is a subject for biophysics, not for astrophysics. And actually, physics is astrobiology. I mean, that term was coined. I can remember when Dan Golden, the head of NASA, coined that term, must be about 30 years ago. When he asked at a conference of astrophysicists, he said, how many people have a biology background? And only 4 people put their hands up. And he said, I want in 5 years' time to make astrobiology as big as astrophysics. It has not become that, but there's a lot of people now, I think, basically, even with the James Webb telescope, one of the primary things that they are trying to discover is whether they can identify signs of life on other planets in other solar systems. And that is a lot of astrobiology. Consciousness is another level, which I think you have to, I personally think of it as us being like a radio set or a computer, right? And if you give Marconi radio, sort of a radio, before Marconi, if you gave a physicist a radio, he would have known exactly how the radio worked, how forget about not a transistor radio, but give him a vacuum tube radio, he would have known exactly how it worked, but he wouldn't have known where the music came. And I think we are in a state like that. We know a lot about the biological, about our brain and everything and how our body works, but we don't understand consciousness. Maybe it's another dimension. Who knows? I have no idea. I keep my brain open on this subject. I have, in fact, argued with Abraham Kaur on this subject, and he sort of shut me up, saying, you can't be a rationalist and believe that there is something beyond that science does not understand. And I disagreed vehemently with him, because I think there are a lot of things, including consciousness, which science does not understand. And what I was talking a few minutes ago as to how people may be having power over life and death of their own life and death. Maybe consciousness has some power over you, which you don't really understand fully. And I have heard of many examples like that. And I think there is some truth in that, that you maybe have your ability to live may depend a lot. I mean, that's how we don't understand how the placebo effect works, right? And therefore, how does it work? And it has to be something that to do with the brain that makes the placebo effect work. We know what the placebo effect is, but we don't know why it works.
And the
Thank
mere
you
fact,
so much.
and the mere fact that we cannot explain does not mean that it's done by some unknown force.
Yes. Because
just that at this stage we don't know.
There was a lot of things which we did not understand 150 years ago, which we now understand how it works, including how the sun produced energy, as something as so fundamental as how the sun produced energy. Right? I mean, now any O-level kid will tell you that, how it does it. But 150 years ago, nobody knew how it did it. And Galileo didn't know it. Newton didn't know it. Einstein hardly would have known it only in his late years. So I think we have to know that the amount that we know now is most probably much less than what we don't know and what we will hopefully discover in the next 150 or 200 years or even 1,000 years. So I think I have no problem with saying we don't know, and hopefully we'll know. And biology is only just starting to become more mathematical and more scientific. It was zoology and botany was very empirical till the 1940s.
Okay. Any other questions, comments? No. Right. So it is my honor and privilege to thank you, Kavan. And as I expected, this happens to be a wonderful program, which is quite fitting for our 100th program. And thank you very much, Kavan, personally from me. And as we usually do, shall we all unmute at this stage and put on your videos and then we'll thank our speaker, Dr. Kavan Ratnatunga, in our usual way. Thank you. Okay, that concludes this episode. Thank you very much.
Thank you very much.
Thank you. Thank you.
Thank
All right.
you.